Thank you, Thiani. Thanks, everyone. So it's really nice to come back to ASIAA, where, as Thiani said, I have many friends and many collaborators. So I'll be talking about mainly the work of two of my former students, Haifeng Yang, who's on faculty of Zhejiang University now in the mainland. Actually, Daniel Lin is actually formerly a research assistant here with both, I think both Chen Fei and Si Wei. So this is talking about disk polarization. So I will give you, since we do have a fair number of students here, I'll give some just introduction about why we actually care about polarization. So the original motivation is to look for magnetic field, which is one of my favorite things to do as well. And I'll talk about the pre-ALMA era, so the polarization in the disk, specifically to look for magnetic field, was actually achieved with CARMA and SMA, in fact. And then it just turns out that on the disk scale, the interpretation was not magnetic field. So that led us to think about the scattering. We were not the first one to do this, but I think our group, together with collaborators, moved the field forward in different directions. So I will talk about some principles first, and talk about the power of using polarization to learn about the physics of the dust grain, and in particular the size and the settling. And then I will summarize some of the observation in the ALMA era. So essentially this field is exploding because of the ALMA, because of high resolution, because of the polarization capability of ALMA. But that actually leads to a lot of confusion as well. So in the last part, so this is a very recent work, so I will give you a sort of the summary of what I think, what this the mechanism of producing the polarization is. And I will try to convince you that at least in some well-defined cases, you may be looking at elongated, specifically a prolate, so sort of needle-like structure that's aligned in the azimuthal direction. And we call this toroidal or oriented prolate grains, or the top grains. So these are the good grains for the polarization. And then I'll try to summarize it. So as I mentioned, that as a theorist, particularly from University of Virginia, you have to believe in the magnetic field in driving the disk evolution, because the so-called magnetic rotation instability, of course, it was invented at Virginia by my colleagues, Barbers and Hawley. So for a long time, and people still believe that if you have a disk, if you want to lose angular momentum, magnetic field is one of the few ways you can do that. Now, so that's really the driver to measure magnetic field. And magnetic field, there are a lot of people working for magnetic field here. It's difficult to measure, but one way to do that is that if you have magnetic field, if you have irregular grains, then the grain will start to spin up, and they will tend to align themselves with their short axis along the magnetic field direction. So that will maximize the angular momentum, essentially. So effectively, it doesn't matter what shape you have for this grain, as long as it's spinning very fast, along the minor axis, it will basically look oblate, so it's sort of like disc-like. So I want people to keep that in mind, because that's essentially everything you need to know about the polarization by magnetic aligned grains. So if you have this sort of a disc-like oblate grains with their short axis along the magnetic field lines, then of course they will tend to emit more light in this direction than in that direction. So basically you have more electric magnetic oscillation here. So you are polarized in the direction that's perpendicular to magnetic field. So everyone thought that this would be a very simple, great way to measure direction of magnetic field, prove the presence. Anytime you see the polarization, you just flip it by 90 degrees. That's your magnetic field direction. And that indeed is the technique people have been using for relatively diffuse gas. So this is the Planck polarization map of the basic old sky. And you rotate it by 90 degrees, and that's magnetic field direction. So this is a galactic plane, and so you basically have magnetic field everywhere. So that's direct proof that in the certain medium it's magnetized, which of course is not surprising. But maybe somewhat surprising is that you can actually find your favorite molecular clouds, Orion, Perseus. So all of these molecular cloud waveform stars, they're threaded by magnetic field, and sometimes there's a order component. So at this point, there's no argument that all these star forming cloud, they must be magnetized. We don't know how strongly, but magnetic field is there. So something you cannot ignore. Now you can actually zoom in and go to individual clouds. So these are vectors from the polarization Planck again. So this is the torus cloud measured in tens of parsecs. You can actually see this magnetic field threading through it. Now, so this magnetic field will go to all different scales. So if you zoom in onto the smaller scale, so this will be individual cores of molecular cloud on the sort of 0.1 parsecs. So they are still magnetized. You can still see the polarization. And you can actually, in some cases, you can measure magnetic field strengths. So again, there's no question that magnetic field is on all kinds of scales that's directly involved with star formation. And even once you form a star, if you zoom in on one of these cores, they will drive jet outflows, and you can actually trace the magnetic field all the way to the central region. So this will be sort of solar system kind of 100 AU scale. So certainly on a few hundred AU scale, 1,000 AU scale, the magnetic field is not only there, it's actually pinched by the collapse. So it's actually interacting with the gas. So you can sort of imagine that the collapsing flow that's feeding or growing your star, your disk, may be dragging the magnetic field. So it's very natural to expect magnetic field to be on the disk scale as well. So you will have magnetic field to drive the outflow, to drive the disk evolution, so on and so forth. So it's not crazy to expect magnetic field there. So the question is, how do you actually measure it? Do you have polarization on the disk scale? So again, even before ALMA, in this very famous source, there was a measurement. In fact, there's even SMA measurement before this, but I will just show you this one. So obviously, this is later on the famous disk. But before you resolve the disk, so this is the CARMA observation by one of my collaborators, Ian Stevens. So he measured in the HL tau with CARMA, so this is before ALMA, the polarization. The polarization is actually in this direction, along this minor axis. But at the time, because people are actually looking for magnetic field, so immediately they flip it by 90 degrees. So this is the magnetic field direction, and we actually find magnetic field. And everyone was very excited because now people, at least theorists like myself, has been trying to use magnetic fields to do all kinds of things. Now it's there. But the problem is that there are actually two problems. The first is that if this is really magnetic field, if these are lines of magnetic field, you actually put it on a disk that's rotating Keplerianly. So this is rotating faster, this is rotating slower. So differential rotation will just wrap this up into toroidal field very quickly. So this is not the expected magnetic field orientation. So that's the first problem. The second problem is that, in fact, if you have your normal magnetic field, the toroidal field, and if you have aligned grains, most of the intensity of the polarized intensity actually will be in the minor axis, whereas here it's actually the polarization is mostly along the major axis. And the reason for that is the picture I asked you to remember at the beginning. So if you have toroidal field, again, that's the most natural magnetic field inside of this because of the differential rotation. Then all these dust grains will be spinning very quickly with short axis along the field lines. So there's basically these disks like that. So this is face-on view. So this will be the polarization direction. Now, if you have an inclined disk, which this source is by about 45 degrees, so this is what this dust grains looks like. So along the minor axis, you actually see this disk's edge on. So that will be highest polarization. Along this, in here, if this were edge on, this actually will be spherical. You will be no polarization. So again, the prediction will be that you have more polarization along the minor axis, less polarization along major axis. That's actually the opposite of what that is. So this is the actual calculation of that. So that led us to believe that there must be a new polarization mechanism. At the time when I was involved with this polarization paper, We don't know what happened, but then actually Kataoka pointed out that actually scattering can actually do the work. So that's what I'm going to do for the next maybe several minutes, to just introduce the concept of the scattering and why scattering actually can produce polarization. So the fact that scattering can produce polarization is not actually surprising. In fact, if you look up in the sky, as long as you don't look directly towards the sun, which you should never do, you will see the blue sky, right? So, and that's actually scattering. Light coming from the star from that direction. You look at that, it's not direct sunlight. And that blue light is actually almost purely scattering light, and it's actually almost 80% polarized. So polarization by scattering is very, very well understood. So this is another example, astronomical example. So this is again spatial tau. So you actually have all kinds of small dust grains surrounding it. So this is the I think it's the near infrared light. So if you look at this scatter light, which is basically the reflection nebula, the polarization degree is actually measured in tens of percent, almost like 50%. So that's the scattering-induced starlight hitting the dust grain, scattering in your direction. So there's no question scattering can produce polarization, in fact, very high polarization, high degree of polarization. So the basic physics is also relatively simple. It has to do with the fact that light is an electromagnetic wave, but it's also transverse wave. In other words, if you are propagating in this direction, your electric field is oscillating perpendicular to that direction of the propagation. Here, you cannot have an electric field oscillating in this direction. And that's the key, because if you scatter that initially non-polarized light, so you have electric field oscillating in this direction and in that direction in equal amounts. So that's what we mean by non-polarized light. Now, if this non-polarized light is scattered off this object here, this dust grain, or anything that's actually small, then if you scatter this by 90 degrees, so this is 90-degree angle, so this component, this oscillation is still there. So you can actually have electromagnetic wave oscillate like that, but that component along the direction of the propagation will die away, will be killed, right? So this is a transverse wave. You cannot have oscillation there. So scattering by 90 degrees, you get full polarization, 100%. So that's actually part of the reason, right? The reflection everywhere is so polarized. Now, on the other hand, if the scattering is by 0 degrees, that's not scattered. Then basically you have, along the same direction, you have the same thing, so this polarization. So 0 polarization, 100 degrees by 90 is 100%. And somewhere in the middle, you polarize by something that's a cosine, essentially some combination of cosine. So again, the most important thing is that the maximum polarization is scattering by 90 degrees. If you're less than that, you will still be polarized, but less. So if you just use that, you can actually explain what we just observed in the CARMA era. So for example, if you have a disk, if it's warmer here, if the temperature decreases, there'll be more light in the central region. So at any given location, the light, most of the light direction will be going in that direction. So if you have dust grains here scattered there, will be scattered perpendicular to that. So the direction of the polarization is really perpendicular to the plane of the scattering. So this is the incoming light, and this is the outgoing light. So these two lights form a plane. So the scattering is always perpendicular to that plane. Perpendicular to the scattering plane. For example, the scattering here, so that's the scattering plane. You have more light in this direction, so it's perpendicular to that plane. So with that, so you can explain, for example, if you have an anisotropic light that's going radially outwards, if you scatter it and you see it in that direction, so this will be your scattering plane going here, and the polarization will be perpendicular to that. Now, if you have light at this very center, then of course this is a face-on view axisymmetric system. You have light coming in this direction, it'll be scattered, this will be your polarization direction. If you have light coming in this direction, scattered by 90 degrees, it'll be perpendicular to this, be in this direction. But if the light coming in equally from all directions, of course, you don't get any polarization, so it gets 0. Now that's the simplest case. Now if you tilt the disk, so if the disk is not face on, if it's inclined, say by 90 degrees, by 45 degrees, Then something interesting happens. So the light that's coming in along the major axis going down, it will scatter into your line of sight by 90 degrees. So light coming in this direction will produce full polarization, the maximum polarization. The light going this direction will be providing maximum polarization here. Now the light from the sideways, now it's not scattered by 90 degrees, it's actually scattered. So if I tilt my hands here, the light coming in this direction will be scattered to your line of sight by more than 90 degrees. And light from the near side scattered by, to the center, and to you will be scattered by an angle that's less than 90 degrees. So the light from near side will be scattered by 45 degrees, and here will be scattered by 135 degrees. But scattering, if it's not 90 degrees, your efficiency will not be 100%, it will be less. So that means the polarization, which is in the vertical direction here, will be smaller than the polarization in the horizontal direction. So this is 90 degree scattering maximum. This is 45 degree scattering less. So the net polarization then is along the minor axis. So that's the prediction. So this is the inclination-induced polarization. And that will be along the minor axis. And in fact, you can do the calculation just to confirm this. So this is a face-on disk. If you do the calculation, you get the polarization as circular towards the edge. So that's just light coming in, scattered by 90 degrees in that direction. At the very center, you get 0, as we would expect. And if you tilt the disk, you get the polarization here along the minor axis, except very close to the edge where the radiation is streaming out radially. So you get anisotropic radiation that's been scattered. Then you're trying to get this azimuthal pattern, but part of that will be canceled by this uniform pattern. So that's why you get less polarization here, because the anisotropic part is going in this direction, the inclination part is going in that direction, so they're perpendicular, so they cancel out. Whereas in this, along the major axis, the scattering part is in this direction, the anisotropic part is also in that direction, they add together. So that's why the major axis has more polarization. So it's actually shaped like this. So both of the most important features that you observe can be explained naturally just by this simple geometric effect. So that's the actual calculation, that's the comparison. So it's a very clean explanation. The bad thing about this when this came out is that everyone was disappointed. Simply because now people spend a lot of time trying to catch the polarization on this scale. They thought they actually measured magnetic field. But this means that this is not magnetic field. So it's not clear you can actually use the polarization to measure magnetic field, certainly not in this particular source. But the good news is that in order to scatter efficiently at the millimeter, so we're talking about the ALMA millimeter arrays, you need large grains. So if you have tiny grains, your scattering efficiency will be very small. So the scattering efficiency, the basic rule of thumb is that it's proportional to the volume of your grain. So if you double the volume, your efficiency will increase by a factor 8. So this is scattering efficiency. So if you have millimeter observing photon, in order to scatter them efficiently, you have to have the size that's roughly speaking about 10 times smaller than the grain. If you actually go beyond the 10%, then other effects will come in. So this is normally called the Rayleigh scattering regime, and this is called the mirror regime. So that's the peak. So, but if you want to have 1% polarization, which is what is usually observed, you need to have basically something here. This is actually about 1%. So if you actually look down, you need grains that's on the order of essentially 0.1 millimeter. So if you observe at 1 millimeter, you need grains roughly about 0.1 millimeter. So that's the power. So this is an independent calculation by Kataoka's group, who actually originally pointed out this idea of the scattering, and we show that this actually can produce the pattern. So this is important because if you think about it, 0.1 millimeter sounds very small, but the interstellar median grain is 0.1 micron. So this is bigger than that by a factor of 100 in size. In terms of volume, actually it's bigger by a factor of 1,000,000. So this is a really large grain compared to what actually is in the envelope. So this is a direct evidence for the grain growth. Now, you'll ask why the grain growth is important. There are many ways to think about it. The one thing, of course, if you want to form planet, you need to decouple the grains from the gas. And if you have small grains, you will not be able to decouple. If you have larger grains, they can decouple by settling. So that's one way to concentrate them. And they can also migrate radially. And they can actually start to concentrate in gas features. So again, this is probably the crucial initial step in the planet formation. So let me now talk about how to use the scattering to probe the settling. Whether or not the grains are mixed with the gas. We all know that the gas is actually not very thin, right? It's thermally supported at some thickness. So the question is whether the dust actually does the same thing. The idea here is that for the inclination induced scattering, if you have dust grain, so this is just a cartoon of the disk. If you have a certain geometry, certain thickness to it, then if you look at from above, for example, for this inclined disk, then you'll be looking at the near side surface at one angle. So this will be your inclination angle. And this will be your far side. And this angle actually will be smaller. Again, this is just pure geometry. So the near side, you will have larger inclination-induced polarization. The far side would have less because you are seeing something that's more face-on. So you can actually you can actually do the actual calculation. So this is an inclined disk. So the polarization intensity is much higher on the near side than on the far side because near side, again, is tilted more away from you. Now, in fact, if you have large grains, for example, if they all settle into the midplane, so they have infinite thin sheet. So as I indicated here, then to your line of sight, this angle here will be the same as the angle here. So there's actually no difference. So then there will not be any near far side asymmetry. Just by looking at the near side far side asymmetry, you can actually tell how thick that layer is. So this is one example of the one case where the near side has more polarization than the far side. So you will say, how can you tell which side is near side, which one is the far side? So it turns out that most of these disks, they actually drive outflow. You can measure which side is actually redshifted, which side is the blue shifted in terms of outflow. So that's the geometry. So this is the outflow going away from you. This is towards you. That's blue shifted, that's red shifted. Now if you're looking in this direction, if the outflow is red shifted, that's superposed in the sky, on this side, this is the near side. And that's the far side. And indeed, this is the near side, and there's more polarization on that side. So this would be an indication that, at least in this particular disk, the dust is actually not settled. It's actually sort of flare like this. So that means you have yet to concentrate the grains to a large enough extent, perhaps, to start to form planets and so on and so forth. So that's an introduction of what you can do with polarization. What is the scattering? So as I said, that this field really exploded immediately after ALMA, and you can probably recognize a lot of names here, and some from the ASIAA here. So this is actually not a complete list. So this is just the early proposals that I was involved with, and actually more. So now some of the so now I'm going to just go through some of the observation with the ALMA. So this is the one case. This is the so-called the IM loop. At the band 7. So band 7 is the highest frequency, the shortest wavelengths the ALMA can actually do the polarization. So this is the shortest wavelengths. So you can actually see, in this case, the polarization vector is along the minor axis. So this is very similar to what you would expect by the scattering due to this inclination-induced polarization. The fact that light coming from the major axis was scattered by 90 degrees, produced maximum polarization in that direction. So that's not the only case. In fact, there's a bunch of other cases, including the HL tau that was originally observed with CARMA. before the ALMA. And now we actually have much better sensitivity. You can actually see, at least at the shortest wavelength, band 7, it's in this direction. And this is another case, you have polarization. So these are the almost surely scattering-induced polarization. At least so far, nobody has been able to come up with an alternative model not involving scattering that will produce this kind of pattern at this kind of 1 or 2% level naturally. So that, the case of scattering seems to be pretty secure, but I have to say it's at this wavelength for these relatively large disks. For other cases, smaller disks, less bright sources, you have some indication maybe the polarization is along the minor axis, but the situation is less clear. Now, you also have actually a few cases, this is one example, where you have the polarization along the minor axis, that's similar to the story I just told you, but you also have this more curved one at the outer edge. So in this case, even though the morphology is slightly more complicated, in principle, you can explain it just using scattering as well, because there are two sources of the polarization. One is the inclination, one is asymmetry of the radiation field. As you go to the edge of the disk, your radiation will be more going radially outwards, and that will produce this azimuthal pattern. So that's at least expected in general for the scattering. But there are still more complicated ones. For example, in this case, as introduced already, so you have this, aligned with the minor axis scattering pattern. You have this, enhancement in the near side. So that's basically a flare disk. The dust is not settled. And then you have this more azimuthal pattern near the outer edge that might be due to just the radial anisotropic radiation. And this is Qin-Fei's work. And it's actually very similar to that one. Although Qin-Fei actually has a better data now, and with better data, the story gets more complicated. But you can ask me about it, but it's not as clean. But in any case, at least in these cases, even though the morphology has various different components, scattering is still reasonable if you take into account the non-settled dust and the anisotropy in the radiation field. Now, it would be nice to provide independent measurement or independent evidence of scattering, because we are really making a big claim here that this millimeter light, they actually scatter off very large grains. The polarization is a good tracer, but it would be nice to have independent evidence for that. So the best evidence that I know of is from the so-called spectral energy distribution. It's just measuring the continuum intensity at different wavelengths and draw a power law and get the power law index. So this is usually the definition. This is the intensity, the frequency, and this is the alpha. Now this alpha usually is larger than 2. And you can get this 2 when the disk is optically thick. And if you have a given temperature, so we all know that if you have an optically thick object, that's at a given temperature, then you're basically looking at black body. Now this is, we all know that this is a black body formula if the at relatively long wavelengths, short frequency. So this is mu squared. So in a black body, you get 2. And in general, it will be very difficult to go below 2. You cannot be more opaque than a black body. But yet, in some observation, in this particular case, where there is already evidence for scattering from the polarization, in the central part, this alpha is actually, this is 2, it's actually less than 2. So the question is why? So it turns out that the scattering can do this, and it relies on very specific property of the scattering. So normally, so this is essentially the Rayleigh scattering, the same scattering as the air molecule produced in the blue sky. So if you have a small object, it will tend to be able to scatter shorter wavelengths, higher frequency radiation more efficiently. So imagine this is the frequency, and this is your brightness, and this is your limit 2. Okay? Now, if you can scatter, so what scattering does to your brightness is actually would reduce the brightness, would diminish it. So if you can scatter more strongly at larger frequency, shorter wavelengths, you can suppress this more compared to the longer wavelengths. Then you can actually flatten this to be less than 2. So that, if you can prove that, then that would be additional evidence for the scattering. So in fact, that's actually exactly what we did. So it turns out that if you were to calculate the opacity or efficiency of the grains that can absorb and scatter, so these are the so-called the black lines. So let's just look at the relatively large grains here, just the black lines. So this will be the absorption opacity, and the dashed lines and dotted line there will be the scattering one. So for these kind of grains, you actually have more. You can scatter more efficiently. So the black dashed line is higher than the black solid line, and more importantly, you can actually scatter more efficiently at band 7, which is the shorter wavelengths, higher frequency one. So that's exactly what we need. You basically suppress the band 7 more compared to band 6. You suppress the shorter wavelengths compared to the longer wavelengths. So that's how you get that. So you can actually do the actual calculation, and this is what the Daniel Lin did for this particular case. So that's the radius, and this is the spectral alpha. And after the convolution of the beam, the inner part is actually below this too. So you can actually match this. So that's the independent evidence that the same scattering not only produced the polarization, but also changed the spectral index and pushed it into a parameter regime that's not accessible without scattering. So I think that's pretty strong evidence for the scattering. But unfortunately, scattering does not explain all of the data, and we have lots of data. So one of the early indications that scattering may not work is the work of Kataoka. So this is a transition disk, and this is the polarization, which is a huge hole there. So that's the polarization vector. So it turns out that this part you can produce using pure scattering. But this southern part, if it's scattering, it will be looking like this. But the actual observation is actually almost a radial. And furthermore, for this part, the polarization fraction is about 10 or 15%, whereas this is about 1 or 2%. So that's scattering, and this is something entirely different. So we don't really know what this is. This is probably aligned grains, maybe actually aligned by magnetic field. So if you imagine if you have toroidal field, so that exactly will work. So this might be one of the cases where you do have toroidal magnetic field aligned grains, but it does not have to be magnetic field that's doing alignment. Now, and this is the further evidence that scattering alone cannot explain all of the polarization data, particularly polarization at the longer wavelengths. And in the ALMA language, of course, this will be smaller numbers here. Band 3 will be 3 millimeter, whereas the band 7 that I've been talking about will be about 0.9 millimeter. So that's the band 7, that's classical signature of the scattering. But at the wavelengths that's about 3.5 times longer, 3.1 millimeter, the polarization pattern is completely different. And this is not due to scattering. And there are several reasons for that. One reason is that if you have relatively small grains, the scattering is really, so in the so-called Rayleigh regime, as you go to longer wavelengths, if you have same grain size, the efficiency of the scattering will drop like a rock. It will really drop like a power law to -4. So that means if if you increase the wavelengths by a factor 3.5, you -4. So that's actually almost a factor of 100. So you should not actually detect this at all if this is really due to pure scattering by the same grain. And furthermore, scattering will not produce this curved pattern at all. So it has to be something else. So the first idea that people had is the idea by Tazaki et al. They say actually there's a way to align grains by the radiation field. Basically, if you have a grain like this, you push it radiation here, the grains will start to spin, and again it will be just disc-like. So anything that's spinning along this minor axis will be flattened structure. Now, if you have radiation that's going from the center going away, then you start to spin these grains. So this will be grains. So you can actually produce polarization that's mu. So in this face-on view. So unfortunately, this actually does not work in the inclined disk. And the reason for that is now these are the grains. If you actually spin them up, and this will be the disks. Now, so the grains. So on the long axis here, you're basically looking at the grains, edge on. So the polarization will be the highest. But here, you can see right here. So you can actually see, on the short axis, the grain will be rounder and rounder. So the prediction of this model will be that you have more polarization along the minor axis, then you have less polarization. You have more polarization along the major axis because you're seeing this edge on, less polarization along minor axis. And so that's actual calculation based on that. And that actually does not look like what is observed. So that idea did not work. So then the question is, what actually could work? So this brings me to the last part of my talk, and this is very new. So we think that this is there's evidence for what we call the top, the good grains. So these are the azimuthally aligned grains, but it's prolate, it's not oblate. So it's not spinning along its a minor axis. So the one piece of evidence for that is the multi-wavelength observation. So for the HR tau, now we actually have all the bands that offers the polarization. That goes from the band 3, the longest wavelengths that ALMA covers the polarization, to band 7. So that's 3, 4, 5, 6, 7. And this is actually VLA in the centimeter. It does polarization too, but the sensitivity is not great. We only get a few vectors. But if you actually stare at this, the pattern is actually very continuous. You can actually see as you go from the long wavelengths, that's azimuthal, go to slightly shorter wavelengths. It will be basically still azimuthal, but then some vectors starting to be more aligned on a minor axis. Then you actually transition. You transition to here, then you actually transition to here. So this clearly indicates that there are two mechanisms that's changing continuously as you go to longer or shorter wavelengths as the wavelengths changes. So we think that this is an indication of all these grains here that's doing the polarization are these kind of grains, effective prolate grains. So this could be irregular grains. If it's irregular grains, it has to be aligned with the major axis, the longest axis, in the azimuthal direction. Now, so this single type of grain can produce both this pattern and this pattern. So that's at least our claim. If you vary the optical depth. So the fact that you're seeing this at different wavelengths, seeing different pattern, is because at the long wavelengths, your optical depth is low. You can see through things. You can see all of the grains. And as you go to more optically thick region, you can only see in the surface layer. And not only that, so the direct thermal emission. So these elongate grains, if you can see each of them, they will emit thermal emission that's polarized. So that will be this pattern. In the optic thin region, you'll see that. And it can have very high polarization fraction depending on the extent of the distortion. Will be like this. As you go to higher optical depths, this actually will drop. I will not go into the exact details of that. This is basically the reason that you see the polarization of these elongate grains is because the emission will be much stronger along the long axis, but at the same time, the absorption will be stronger along the long axis as well. So if you actually go to larger and larger optical depths, these emission and absorption actually will cancel out. So you actually get, if the temperature is the same, you get zero polarization in the optical thick region. So the direct thermal emission from these aligned grains will decrease as you go to either higher wavelengths, where the optical depth is higher, or the region that has larger column density, which I will come back in a second. Whereas the scattering also depends on the optical depth. In fact, the scattering is optimal around optical depth of 1, so that you get maybe a little bit more than 1%. but it does not drop to 0. So even if you see the surface layer, this inclination effect of the scattering will still be able to produce about 1 or about 0.6%. That's the kind of level you observe. So our claim is that in fact, you can actually decompose these azimuthal all the pattern into the azimuthal component and the parallel to the minor axis component. And this is what we get. So if you go to a shorter wavelength, so this will be your band 7, and this will be band 3. So this will be very optic thick region. This will be very optic thin region. In the optic thin region, actually in band 3, long wavelengths, you're almost completely dominated by the direct thermal emission by these aligned grains because you see all of them. You produce a polarization that's a few percent. Now, if you go to shorter and shorter wavelengths, then the contribution from the thermal direction, thermal emission will be less and less because of the extinction, but the scattering stays relatively flat. So going to shorter wavelengths, the scattering dominates, and that's why the pattern is what you expect from scattering along the minor axis. So that's a reasonably consistent story, but this is probably the clincher. Okay, so this is published, I think, earlier, late last year. So this is by far the highest resolution polarization observation of any disks. So in the early times, if we get a few vectors, we'll be very happy. But in this particular case, you get more than 2,000 vectors on a single disk. And if you look at it, so this is, again, Zhi Yun is famous because of the rings and gaps. So in the background, it's actually the continuum. So that's continuum. So that's a ring, that's a ring, that's a gap. The dark region is the gap. So if you actually just stare at it, the polarization pattern and behavior is actually different in the rings and the gaps. In the rings, the polarization fraction is actually lower. In the gaps, you can actually see this vector that's longer. And furthermore, in the gaps, you actually get this azimuthal pattern, almost like this bracket pattern. And also, you have more polarization along the major axis. You have less polarization along the minor axis. So it turns out that all of these major features you can explain by the same idea, is that underlying all of this is that everywhere you have these prolate, needle-like, if you will, grains that's aligned azimuthally, so like this. And the reason that you see different things is that in the gap, your optical depth is lower. So you are seeing intrinsically these azimuthally aligned grains. And whereas in the ring, it's denser column density, your optical depth is larger, you're only seeing the surface layer, and you have lower polarization, and the polarization pattern is along the minor axis. So that's very consistent with the story I told you based on different wavelengths, which also have different optical depths. And in fact, we did a calculation, or I should say that Daniel Lin did the actual calculation. So this is actually the model. It produced all of the major features, like the more polarization in the gap, the different directions. And furthermore, you have more polarization along the major axis for the same reason, because the polarization for the aligned grains is in this direction, and the scattering is also in this direction. So along the major axis, the two mechanisms add together. But if you are here on the minor axis, polarization from the direct thermal emission is in this direction, scattering is actually in that direction. So you actually cancel out. So that works out as well. So the real question is, why do you have grains that behave so crazily? They were actually aligned in the azimuthal direction with long axis along the. So this is something that Daniel did, and this is the idea that he came up with. Apparently, Daniel probably is pretty good at the badminton. So I want you to look at how the badminton birdie flies. Now you hit it, the birdie will be flying and it will be aligned. So initially the angle could be, the birdie could be any angle, but after a while the birdie will be the head first, the tail be back. So if you're moving in this direction, the birdie is always aligned. So in fact, the dynamics, the physics of this is so interesting. There's actually a paper describing how the birdie would eventually become aligned with the direction of the flight. So initially, so this is the direction of the flight, and there's an angle, let's just say called phi. So when you hit it, of course, this can tumble, this can do anything. And this angle, it turns out, will oscillate. And the angle of the oscillation, the amplitude of oscillation actually will decrease with time. So this is the high-speed camera, obviously. And this is that measurement of that angle. And this is, you hit this twice, you get different result, but eventually you get the same behavior. So that's that angle initially. It's huge, maybe even opposite misaligned the oscillation very quickly. The amplitude damps. And this, this is phi equals 0. What does phi equals 0 means? That means this birdie, the axis of that is along this direction of motion. So that's alignment. That's real alignment by aerodynamic drag. So this is essentially what we have in mind in a paper that was published. Well, actually only accepted. It's not even published yet. So we are imagining that these little grains, irregular grains, are really just like the badminton. And if grains are large enough, they'll be moving on Keplerian motion. Right? They are not gas. They don't experience the gas pressure. And the gas, of course, because they experience the pressure gradient, they actually do not move at exactly Keplerian speed. They'll be moving at sub-Keplerian speed. So that means these large grains will be plowing through in an azimuthal direction, moving through relative to the gas, and they'll be basically blown back like the birdies. So that's the sort of the mental picture. And Daniel actually did a lot of analysis, did actually calculation. But the basic idea, just explain the physics a little bit more. So if you have a badminton that's spinning, that's moving, tumbling, in this kind of solid body dynamics, usually you do two things. You decompose the translational motion, the bulk motion of that body, okay, and then relative to the center of mass, you do have this rotation or spinning. So it turns out that this oscillation and the damping, both of them are because of the motion relative to the air. You experience a drag. So this is aerodynamic drag. So if you, for example, if you have for this bulk motion or translation motion, if initially this is misaligned like this, now for this feather, for this tail, of course the area here will be larger. So your drag force relative to this motion, this drag force actually will be larger. You have a drag force here too, that'll be smaller because the head is smaller. So the net force, the net torque relative to the center of mass is actually in this direction. So you have this that's forcing this angle to be smaller. This is what is forcing the alignment. So this is the restoring torque. So this is the reason why you actually have oscillation. Similarly, if this is aligned this way, then your tail is here. Your air will be blowing on this. This is a larger force, and this smaller force, it will have a torque in that direction. It will try to force this to go back to the equilibrium. So this is how you get the oscillation part. Now, if now you have this birdie that's rotating, that's moving relative to the air, of course, any motion through the air would have resistance. You will have to drag. So there's a drag force going this direction, and that's resisting this rotation. So that's why this spin, this oscillation will be damped, simply because of this drag force. So again, the head is moving in this direction, the drag force is in that direction. So this rotation is damped. So this is really just a damped oscillator. So the only requirement is that you cannot have a uniform spherical grain. If you have spherical grain, nothing will happen. There will not be any torque. So you have to have a regular grain, and the center of mass will not be exactly at the geometric center. So basically, that's the requirement. That's sort of the requirement for the birdie as well. Now, then you can actually calculate the time scale, which I will skip all of the math. So essentially, the time scale for the damping of the oscillation So the oscillation amplitude is getting smaller and smaller. There's a time scale associated with that. So that damping time scale, of course, is alignment time scale. So it turns out that it's a dimensionless quantity that depends on the shape. The more irregular you are, it will be damped more quickly. And if the closer you are to a sphere, it will damp for a longer time. But in general, this is a factor of maybe a few to maybe 10, maybe in extreme case it could be 100. But these are the things that depends on the property of the grain. So this is the material property. This is actually 3 grams per cubic centimeter. So this is the sand density. And this is the size of the grain. This is the gas density, which is usually very, very small in the disk. This is basically sound speed, thermal speed of the molecules that's doing the damping. Now, people working in the disk dynamics will recognize this combination immediately. That's actually the stopping time. The stopping time is defined as this combination. That's basically any motion you move with in the disk through the drag. Any initial momentum you have, you'll go to almost 0 because of this drag force. That time to stop your motion is the stopping time, and that's simply proportional to the density of the grain, inverse of the gas. And the stopping time in the dynamics of the grains is usually written as the Stokes parameter, dimensionless parameter. Basically, the stopping time normalized by this omega here, which is of course the rotation period at a given location. So the damping time is really written as the orbital period times the Stokes number, and this is the order of unity factor. So if you have a grain with small Stokes number, and most people believe that, at least at the for the kind of grains you can probe, these are probably at most unity, maybe less than unity most of the time. So that means these oscillations will be damped on the orbital time scale, which is extremely fast. So that's the alignment time scale. And you can also estimate the oscillation time scale. Again, I will not go into the derivation here, which is related to the gas density relative to the grain gas density. So this is much larger than that, which means that the oscillation time scale is very short. So basically you have very short, you have very fast oscillation, and the amplitude will start to damp. But even this damping time scale is the orbital time. So that's our picture. Again, this is so new. There's probably all kinds of things we have not thought about. But that's the beginning of the story, I think. So let me try to summarize here. So again, this field is really, driven by ALMA data, and we have a fair amount of it. So even though initially we tried to look at, you try to use the polarization, look for magnetic field, and in some cases the magnetic field may still be there, maybe doing alignment for, a few cases, but still there's a potential for using that. But I think the field is now moved towards using it to probe the grain size, the grain shape. And if you believe in Daniel's interpretation, maybe the relative motion of the dust grain to the gas, that of course is involved in concentration of the dust, the planet formation. So that's why this actually is important. So I think I showed you the evidence. I think it's pretty strong that, at least in some cases, at short wavelengths, this regular pattern can only be produced by scattering off of reasonably large grains, about 0.1 millimeter, but that depends on assumption of the grain size and shape. So there's all kinds of uncertainty with that, the exact size and shape. But I think I also showed you the evidence that in certain cases, because of the observed asymmetry, you can infer that these grains are not infinitely thin. They are not set at the midplane. If they did, then you would not actually expect this near far side asymmetry. And this near far side asymmetry is because of the flaring of the dust layer, not the gas layer. So that when you look at it from any direction, the near side and far side would have different angle to you. And most interestingly, probably most excitingly, I think there's evidence for these, what we call the top. This will be the toroidally aligned grains. That's sort of like this, both from the multi-wavelengths observation and from this very high resolution observation. And that might be produced by something that's similar to the badminton here. So let me actually stop here.
All right, questions? Yes. So he got
down by gas drag, doesn't gravity pull them into the sentinel?
It would try to do that, but once you get to the new orbit, it will be spinning up. It will actually, probably get worse, right? You will lose some angular and you shift to the lower orbit, right?
But then you still get, it's very, like every orbit you get useful down to the gas speed. So as you go again,
Yeah.
you're always moving at the gas speed.
No, you're not. You're trying to move at gas speed at some time scale. So there's the.
You think it's the orbital time? That's very fast.
Oh no! Sorry. Yeah, it's you spin down. The alignment occurs at that time.
No, but your T stop. Isn't your T stop the time it takes to move at the gas speed?
Yes.
So after that, we say it's orbital time, and then the T oscillation is even shorter. So you oscillate many times in an orbit, and then.
Right. So let me try to understand the argument here. So these grains, of course, some of the grains, particularly if the Stokes number is actually off order unity, they do move, they do actually drift. Their orbit is actually like this, if this is orbital one. So it's really the small grains and the large grains. Really small grains, they will move with the gas at subcurrent speed. Really large grains, they don't care, they'll be saying that. So I think what you're saying is in a case that's probably, on over unity, they are more complicated. They do actually, do what you say. But what I'm envisioning is larger grains that, do not really experience the gas drag. They can experience gas drag, but gas drag does not do much to remove the angular momentum. So that's where the relative drift will be at mu-cell. But there are all kinds of complications there because the gas has substructure. Then the gas velocity, it can be it can be subcaplarian, it can be supercaplarian. So it can get complicated very quickly.
Okay.
Yes.
Yeah, thank you. I actually have a few questions.
Yeah.
First, okay, so you show the plot for thermal emission versus scattering. So,
Yeah. Yes.
Okay, those kind of curves or degree of polarization with the scattering and the millimeter color
Yeah.
depend on scattering algorithm. My question is, so what kind of scattering algorithms do you assume, and what is that based on? So that's based on what that its uncertainty affect the analysis.
Yeah. So here, in fact, so this curve, they actually there's no assumed beta or anything. So this is straight from decomposing the scattering, the observational pattern, right? So you have this pattern. So you know that it's mostly just this dot here. So the polarization fraction is about 2%, and it's all circular, and that's mostly just thermal emission. And then you know that in this case, it's mostly just the scattering, it's just pattern here. But you can actually start to see a little bit of curvature here. So you know that there's a little bit of a smoother pattern that's mixed in, but at the level that's maybe less than half. But if you actually look at a pattern like here, this will be band 1.3. That will be one of these bands. So if I can look at this will be some sort of in between, half and half. So this is strictly a decomposition of the orientation. Did not even assume anything about the scattering efficiency or beta. Then you can try to interpret this. What kind of grains can do this? Can scatter a little bit more at shorter wavelengths, and a little bit less at longer wavelengths. And this is the funny thing. This is actually important. If this is really very small grain, if the scattering is really, the curve will be like this, right? This is lambda to -4.
Yeah,
This is
I still think that when you scattering algorithm for analysis, but we can calculate the beta.
right.
Anyway, the next question is, so you say, you see a signature of geometry 6
Yeah.
not super thin. So
Yeah.
for P object, and in case for HH 80 and 81, so it's a high mass object.
Yep.
In case for low mass object like digital and HH 111, so what will be the estimated thickness?
So first of all, if you stare at this there's very little evidence for the near side brighter than the far side. So this just tells you right away it cannot be very thick. It cannot be as thick as, for example, the gas. Right? The gas, have some, geometric thickness. So it cannot be like that. So this is, direct evidence that the dust that's doing the emission, in the minimum emission, that's doing the polarization, has already settled in the midplane. And you can try to constrain the degree of the flaring that you can get here. And we have not done that. And we don't think that the data, is enough quality to do that. But maybe you will be able to. In fact, the iPhone, the first student I mentioned, is trying to do that for the much better data for the edge of tau. So in principle, because you have more vectors, but again, this is a very high resolution. Some of these may be just the interferometer effects. So you might be able to do better there, but still, you can actually try to constrain whether these rings are thick or not. But it's very difficult once you have this, high resolution observation with noise.
Can we move to anti-machine? Okay.
Yeah.
So, yes. So as you said, of course, this kind of measurement has a potential to talk about the grains loss.
Yeah.
But you are not really telling us the absolute size of the grains which we could derive such observations. But do you have any comments on that?
Yeah, it's complicated because, when you do theory, start with spherical grains, right? So if you assume spherical grains, everything's calculable, you get sizes on the order of 0.1 millimeter. And that may still be, a good answer. And the reason is really just because if you go to much larger grains, then you go to the mirror region, then all the scattering property will be different. So all the pattern actually will be changed. So you do not want to go to much larger than 1 millimeter. And if you don't want to go to very small ones, because they will not be efficient enough. So roughly it's probably between 0.1 and 1, okay? But the exact number depends on the shape. You are in a region, you can have relatively large grains with different shape that will scatter, this light, differently. So we cannot give you now. In fact, the more interesting thing is if you believe this 0.1 millimeter, that will be very different from what people say this is 1 millimeter or even 1 centimeter, right? Because this is spectral energy index. So there's a tension there. It's not resolved completely. One way to resolve it is, in fact, and I'm thinking maybe, in fact, the spectral index measurement could be wrong. And this is the reason why. So this is, again, Daniel Lin measured this, this object. This object actually has rings and gaps. It's very famous for that. So this is the calculated spectral index in the gap for grains that's about 0.1 millimeter. And this, so this is the actual calculation, and this is the beam convolved spectral index. So if you look at this, you will say this is interstellar grain, right? Small grains. And for the ring, of course, it's very optically thick. Your beta is, basically is 2, okay? Now, if you actually mix these two together, 2 and the 4, you get 1.3, 1.4. That's this. And when people look at this, they say, aha, this is grain growth. Now, in between the optical thick to that. So that might be wrong. So if your disk has a lot of structure in it, you basically have a mixture of the 2s and 4s, then you get, 3.5. So again, that's, at least that's one possibility. And that's probably true for this particular source.
Okay, last question.
Yeah.
Yeah.
So going back to this grain alignment. It's cool. But you said it relies on the gas and dust having different rotational velocities.
Yeah, different motion. The drift requires a drift, yes.
Wouldn't that vanish in a dust ring because the dust accumulates at pressure maximum?
Yes, that's,
Both of them would have.
yes, it would, it would. Yes, that could be a problem.
You would predict no effect in dust rings.
You may not be able to align anything if the dust stays there, if you actually trap them there. Yes. So I agree with that. And it's something we're starting to think about. Again, this is very new. We want to just get the mechanism. The mechanism, well, is the badminton, right? Nobody can argue that badminton cannot align. And there's the issue of to what extent you have this asymmetry in the real grains, and then to what extent the dynamics of the disk will support this azimuthal drift velocity. And this actually will not work for small grains, right? Because the drift of small grains is actually radial rather than azimuthal. Right. Okay. Yeah. So yeah. Yeah.